In this video, we will be solving sums based on Rolle's theorem and Lagrange mean value theorem. The sums that I've taken are from the Maharashtra government textbook, Mathematics Part 2, 12th Standard, exercise 2.3. Let's begin with the first question. It says that you need to check the validity of Rolle's theorem for the following functions. So Rolle's theorem, Rolle's theorem is going to be valid if the function is continuous and differentiable in the given interval, and f of a and f of b have to be equal. That is, the function value at the starting and the ending point needs to be equal. So if we check for question number 1, in the interval 1 to 3, this is a polynomial function, and polynomial functions are continuous for any given range. So f of x is continuous. Okay, I should write it properly. So it's f of x which is continuous in the interval 1 to 3. Now you need to check for f dash x also. F dash x, that's going to be 2x minus 4, and f dash x is also a polynomial function in the given interval, that is when x values lie between 1 and 3. F dash x will exist at every number that you select between 1 and 3. So we can say that f dash x will exist in the entire interval 1 to 3, and if f dash x will exist, we can say that f of x is differentiable. F of x is differentiable because the derivative will exist at every point in the given interval. So f of x is differentiable in the interval 1 to 3. We just need to write that 1 and 3 in round brackets when we talk about differentiability. And the first two conditions have been satisfied. F of 1, if you put that 1 here, it will be 1 minus 4 plus 3, which is equal to 0. Put 3 also in this same function, and you will have 9 minus 12 plus 3, which is also equal to 0. So f of 1 and f of 3 both are equal to each other, which is basically equal to 0. Equal to 0 is not of that much significance when you check the validity of Rolle's theorem. All we need to check out here is the fact that f of 1 and f of 3, both of them are equal. And because of 1, 2 and 3 conditions getting satisfied, we can say that the given function satisfies all the conditions of the Rolle's theorem, and Rolle's theorem will be applicable for the given function. So yeah, that's how you're answering the first question. And with that, we go ahead with the second question. Let's go ahead with the second question. One thing regarding the statement that they've said here, check the validity of Rolle's theorem. So validity means all that they are trying to ask you is just check whether the Rolle's theorem will be applicable or no. They are not telling you to apply the Rolle's theorem and find that value of x where the derivative will be 0. They are only asking you to check if the Rolle's theorem is going to be applicable or no. That is what they mean when they say check the validity of Rolle's theorem. So let's start checking that validity for the second question. F of x is e power minus x into sine x. Now, as long as x belongs to the interval 0 to pi, f of x is going to exist at every point. F of x is e power minus x into sine x. So whatever value of x you take between 0 to pi, you will definitely get a value for this particular function. And if the value of the function is going to exist at every point, we say that the function is continuous at that point. Under what circumstances will the value not exist? The value for a function will not exist if there is a square root, if you get a negative number inside a square root, or if you get a 0 in the denominator. In such circumstances, the function value will not exist, and we will say that at that point the function is discontinuous. But in this case, no matter whatever value of x you take, you will definitely have a function value, and that is why we say that f of x is continuous in the given interval 0 to pi. Okay, whatever I just stated, it's not an exact way of identifying the functions as continuous or discontinuous, but most of the functions, to a very large extent, you can identify it in this way, that whether they will be continuous or discontinuous. Let's go for finding the derivative. So if you realize, f dash x for that function is going to be e power minus x into cos x plus sin x into e power minus x into minus 1. That will make it e power minus x into sin x. For the given interval, that is 0 to pi, whatever value of x you take in the given interval, the function f dash x is also going to exist. So if f dash x is going to exist at every value of x in this interval, we will say that f dash x is existing, and that is why f of x is differentiable in that interval 0 to pi. For differentiability, we use a round bracket on the specified interval. For continuous or discontinuous, we use a square bracket. The first two conditions of Rolle's theorem are satisfied. Let's check the last condition. F of 0, that will be e power 0, which is 1 into sine 0, that is 1 into 0, which is 0. And when you put a pi here, sine pi will be 0. So anything into 0 will be 0. So f of 0 and f of pi both are equal to 0, and that is why we say that both of them are ultimately equal to each other. So the three conditions of Rolle's theorem are satisfied, and we can say that Rolle's theorem is applicable for the function given to us in second subpart of this question. Going ahead with the third question. The third function, it is a polynomial function, so in the given interval, f of x will be continuous at every point. So f of x is continuous in the interval 1 to 3. That's the first condition of Rolle's theorem getting satisfied. F dash x will be 4x minus 5, which is also a polynomial function. So if f dash x is going to exist at every interval in this, f dash x is a polynomial function, so it exists at all values of x in the given interval, and that is why we say that if f dash x exists, then f of x is differentiable in the given interval, that is 1 to 3. Let's check for the third condition. If I try finding f of 1 will be 2 minus 5 plus 3, which is equal to 0, and f of 3, that is equal to 2 into 9, that's 18, 18 minus 15, which is 3 plus 3, which is equal to 6. And we see that f of 1 is not equal to f of 3. So the third condition of Rolle's theorem is not satisfied, and if all conditions of Rolle's theorem are not, not all, but even if there is one condition of Rolle's theorem not getting satisfied, we have to say that Rolle's theorem is not applicable for the third function given to us. So for the third function, this function, we will say that Rolle's theorem is not applicable because the third condition of Rolle's theorem is not satisfied. Let's continue with the fourth question. The functions sin x and cos x, they are continuous and differentiable over the entire range of real numbers. That's because if you realize the graph of sin x looks like this. There is no break in the entire graph, and that is why you can say that the function sin x is continuous over the entire range of real numbers. The same thing is with cos x, but the graph of cos x will look like this. It's a wave function only. But just that it will start from a different point than sin x. So the graph of cos x is also going to be continuous over the entire range of real numbers. The derivative of cos will be minus sin, and the derivative of sin will be cos. So the derivatives are also functions that will exist over the entire range of real numbers, and that is why we say that the functions are differentiable also over the entire range of real numbers. So sin x and cos x, both these functions are continuous as well as differentiable in the interval 0 to 2 pi. This is only a constant, so that does not affect the existence of f of x. And this is the reason we say that f of x is going to be continuous in the interval 0 to 2 pi. And f dash x also exists in that entire interval. So f of x is differentiable also in that interval 0 to 2 pi. So first two conditions of Rolle's theorem are satisfied. Let's check for the third condition. F of 0, that's going to be sin 0, which is 0, minus cos 0, which is 1. So we have 0 minus 1 plus 3, which is equal to 2, and f of 2 pi, that will be sin 2 pi, which is again 0, minus cos 2 pi, which is minus 1 plus 3, which is again equal to 2. So f of 0 and f of 2, both of them are equal to each other. So the third condition of Rolle's theorem is also satisfied, and we can conclude that for the fourth function, Rolle's theorem is applicable. Going ahead with the fifth one, f of x is x square, and for this entire range of values, f of x is going to exist because it's a polynomial function, Even this is a polynomial function, so in the interval 2 to 6 also the entire function is going to exist and it is going to be continuous. Now whether the function is continuous at x equal to 2 or no, we can check that by applying limits. So the left hand limit, which is x tending to 2 minus, when x approaches 2 from the left hand side, we have the function as x square. So this will be limit of x tends to 2 x square, which will be equal to 2 square, and that is equal to 4. Let's evaluate the right hand limit, that is limit of x tends to 2 plus f of x. That will be limit of x tends to 2. The right hand limit, that is when x is greater than 2. The function for that will be 6 minus x. So when we put x equal to 2 here, we get 6 minus 2, which is equal to 4. So the left hand limit and right hand limit for the function are equal, and that is why we say that f of x is continuous in the given interval, which is 0 to 6. So f of x is continuous in the interval. Now whether it is differentiable or not, we don't know that. In the interval 0 to 2, you take a derivative and that will be 2x. So the derivative is going to exist at every point in the interval 0 to 2. So in the interval 0 to 2, if the derivative is existing, function is differentiable. Similarly, 6 minus x, the derivative is minus 1. And in the interval 2 to 6, the derivative is existing. So the function is differentiable in the interval 2 to 6 also. What about exactly at x equal to 2? If I have to talk about f dash x will be 2x for the first interval. That is when x lies between 0 and 2. And f of x will be equal to minus 1 when x lies between 2 and 6. Okay. Now the left hand derivative, this is f dash x, okay? Yeah. So now the left hand derivative, that's left hand derivative means the derivative for x lesser than 2. For x lesser than 2, the left hand derivative is 2. For x greater than 2, the right hand derivative is minus 1. So exactly at 2, the left hand derivative and the right hand derivative are not equal, and that is why f dash x is going to be discontinuous for x equal to 2. If f dash x will be discontinuous at x equal to 2, we say that f of x is not differentiable at x equal to 2. So f of x is not differentiable at x equal to 2. And that x equal to 2 basically belongs to the interval 0 to 6. So there is one point where the function is not differentiable, and because the function is not differentiable at one point in the given interval 0 to 6, we say that the conditions of Rolle's theorem are not satisfied. So the first condition satisfied, the function is continuous, but the second condition of being differentiable in the given interval is not satisfied, which is why we say that the Rolle's theorem is not applicable for the fifth function that is given to us. Going ahead with the sixth one, x power 2 by 3 in the interval minus 1 to 1, it will exist for all values of x, and that is why we say that f of x is continuous in the interval minus 1 to 1. Take a derivative of this function and you get f dash x, which is equal to 2 by 3 x power minus 1 by 3, and that basically represents 1 upon cube root of x. For every number lying between minus 1 and 1, f dash x is also going to exist, and that is why we say that if f dash x is going to exist for all values of x in the given interval, f of x is differentiable in the given interval, which is minus 1 to 1. So the first and the second conditions of Rolle's theorem are satisfied. We try to check for the third condition. Try finding f of minus 1. F of minus 1, that's going to be equal to minus 1 square, which is 1, and cube root of it, which is 1 only. And f of 1, that will be square of 1, which is 1, and cube root of 1, which is equal to 1 only. So f of minus 1 and f of 1, both of them are equal to each other, which is why the condition, the third condition of Rolle's theorem is also satisfied, and we can finally conclude that Rolle's theorem is applicable for the sixth function given to us. Let's go ahead with question number 2. In a given interval a to b, it is said that the given function is going to satisfy the Rolle's theorem. It is already known that a is minus 1, find the value of b. So if the Rolle's theorem is satisfied, we know that f of b and f of a will be equal. But a is already minus 1, so let's write a minus 1 in that position. F of b, that will be b power 4 plus b square minus 2. and that will be f of minus 1. F of minus 1, that will be minus 1 power 4, which is 1, plus minus 1 square, which is 1, and minus 2. So we have 1 plus 1 minus 2, which is equal to 0. If you try to factorize this, you need to understand it's a quadratic in b square. So if you try to factorize that, you have b square minus, b square plus 2 and b square minus 1 equal to 0. So either b square will be minus 2, which is not possible, so we eliminate that possibility, or b square will be 1, so b will be equal to plus minus 1. But already a is minus 1. So for specifying an interval a to b can't be minus 1. So the other only leftover possibility for b is b equal to 1. So the value of b out there is going to be 1, and with that we go ahead with the third question. Now here you need to verify the Rolle's theorem. So verify means you don't have to only check whether the Rolle's theorem is applicable or no. If it is applicable, then you find that point where the derivative is going to be 0, and you show that the point where you got the derivative as 0, that point lies in the given interval. So for the first function, these are functions of sine and cos. That is, it is enough to tell you that f of x is going to be continuous in 0 to 2 pi and also differentiable in 0 to 2 pi. So the first and second conditions of Rolle's theorem are satisfied. Let's try evaluating f of 0. F of 0 is 0 plus 1 plus 7, which is equal to 8, and f of 2 pi, it's going to be the same because the period of sin x and cos x is 2 pi. So sin 0 and sin 2 pi are going to be equal, cos 0 and cos 2 pi are going to be equal. So sin 2 pi 0, cos 2 pi 1, and 0 plus 1 plus 7, f of 2 pi is going to be equal to 8 only. So f of 0 and f of 2 pi are equal. So all the conditions of Rolle's theorem are satisfied. All conditions of Rolle's theorem are satisfied. And if they are satisfied, then find a point where the derivative is going to be 0 and show that this particular point belongs to the interval 0 to 2 pi. The derivative, that is f dash x, is going to be cos x minus sin x, and the derivative of 7 will be 0, so plus 0. If you equate the derivative with 0, you get cos x minus sin x equal to 0. So when you take that sin x on the right, you realize that cos x will be equal to sin x. And there are 2 points where this can happen. In the interval 0 to 360, this happens at theta equal to 45, so x equal to pi by 4 is one of the values where cos x and sin x will be equal. At the same time, a value like 5 pi by 4, which is 225 degrees, even at x equal to 5 pi by 4, cos x and sin x will be equal. That is, both of them will be equal to minus 1 by root 2. Both these values lie in the given interval. So we say that the Rolle's theorem has been verified because Rolle's theorem stated that if all the conditions of Rolle's theorem are satisfied, that is these 3 conditions, then there will be at least one point in the given interval where the derivative will be 0. We have taken the derivative, we equated the derivative with 0, and we got these values of x, and we saw that these values actually belong to this interval. So in this interval, there are not one, but there are 2 values where the derivative will be 0. And that is how we are verifying that yes, the Rolle's theorem is indeed true for all those functions which satisfy all the conditions of Rolle's theorem. Continuing with the second question. Again, it's sin x by 2. It is a sine function, so f of x is going to be continuous in the given interval, which is 0 to 2 pi. For continuous we use the square brackets, and differentiable in the interval round bracket 0 to 2 pi. Okay, that's simply because it's a sine function. Had it been a cos function, I would have said the same. You can't say the same for tan, cot, sec and cosec. Only for sine and cos it's applicable. It is sine, so I have set this condition. So the first and second conditions of Rolle's theorem are satisfied. What about f of 0? That will be sin 0 by 2, which is sin 0, which is 0. And f of 2 pi, that will be f of 2 pi by 2, that is sin of 2 pi by 2. That is sin of pi, which is equal to 0 only. So f of 2 pi and f of 0 are equal, which is why all the conditions of Rolle's theorem are satisfied. Take a derivative and equate that with 0. F dash x will be cos x by 2 into 1 by 2. Equate that with 0. So you have 1 by 2 into cos of x by 2 equal to 0. So 2 goes there and you get cos of x by 2 as 0. Cos of x by 2 equal to 0 means x by 2 can be equal to 90 degrees, which is pi by 2 radians, or x can be equal to 270 degrees, which is 3 pi by 2. I mean, x by 2 will be equal to 3 pi by 2. So a possible value of x that we have is pi, and the other possible value of x that we have is 3 pi. Of course, I know there are more number of values, but I'm just trying to find out values that lie in this interval. X equal to 3 pi has to be discarded because it does not belong to the interval 0 to 2 pi. So we discard this possibility, but at least the first possibility that we have taken, which gave us the value of x as pi. So the value of x as pi does lie in this interval. So we see that at x equal to pi, that is for at least one value in the given interval, the derivative was equal to 0. And yeah, that's how we are verifying the Rolle's theorem, because in this condition, in this question, the function satisfied all conditions of the Rolle's theorem, and that is why in the given interval we got a point, we got at least one point, that is x equal to pi, where the derivative was 0. Let's continue with the third question. It's a polynomial function, so it is going to be continuous and differentiable in whatever interval they have given. So the first two conditions are satisfied. Let's not separately write that. Let's go for the third condition. F of 1, if you check, f of 1 will be 1 minus 5, that is minus 4, plus 9, which is equal to 5, and f of 4 is going to be 16 minus 20, that is minus 4, plus 9, which is again equal to 5. So f of 1 and f of 4 are equal, and that is why we say that the function satisfies all the conditions of the Rolle's theorem. Let's take the derivative. So the derivative is going to be 2x minus 5. And when you equate the derivative with 0, you have 2x minus 5 equal to 0. So the value of x will be 5 by 2, which is 2.5. And 2.5, yeah, it belongs to the interval 1 to 4. So because the function satisfied all the conditions of the Rolle's theorem, we got a point, we got at least one point in this interval where the derivative was equal to 0. And yeah, that's how we are proving that the third function also satisfies the Rolle's theorem. If Rolle's theorem holds good for the following function, for the given interval, with the value of c being 2 plus 1 by root 3, that means at 2 plus 1 by root 3, the derivative will be 0. Find the values of p and q. So it's quite a simple sum. All you need to do is, you need to apply the third condition first, that is f of 1 equal to f of 3. See, when you do this, you will get one equation between p and q, and later when you apply the second condition, that is f dash of c equal to 0, you will get one more equation between p and q. Solve them simultaneously to get the values of p and q. That's going to be the approach of this question. F of 1, that will be 1 plus p plus q plus 5. That is p plus q plus 6. That should be equal to f of 3, which is 27 plus 9p plus 3q plus 5. 27 and 5 will be 32. We have 32 plus 9p plus 3q, and finally 32. Okay, I think we will take p plus q on the right, so that will give us 8p plus 2q. On the left, it's going to be minus 26. Divide throughout by 2, so you will have 4p plus q equal to minus 13, and that is your equation number 1. For equation number 2, we put f dash of c equal to 0. F dash of c, that will be 3c square plus 2pc plus q equal to 0, and the value of c has been given to us as 2 plus 1 by root 3. So 3 into the square of 2 plus 1 by root 3, right? 2 plus 1 by root 3 the whole square. We will expand it by using the a plus b whole square formula in the next step. 2p into 2 plus 1 by root 3 plus q equal to 0. Okay, so we have 3. Square this entire bracket, so you are going to have 4 plus 4 by root 3 plus 1 by 3 plus 4p plus 2p by root 3 plus q equal to 0. Now 4p plus q is already minus 13, and let's put it in this equation itself. So 4p plus q, let's write it here only, this is minus 13. And try to expand this further. So you have 4 plus 1 by 3, that will be equal to what, 12 plus 1, 13 by 3. So here we have a 13 by 3 plus 4 by root 3. When you expand the full bracket, you get 13 plus 4 into 3, which is 12, divided by root 3, minus 13 plus 2p by root 3. And the right hand side was already 0, so the right hand side is 0 here. 13 minus 13 gets cancelled, and we take this plus 12 by 3 on the other side. So we have 2p by root 3 is equals to minus 12 by root 3. Cancel off this root 3 here and here, and the value of p will finally be equal to minus 6. If p is minus 6, put that p as minus 6 in equation 1, and that will give you the value of q as minus 24. Let that go here, so q will be equal to 11. Yeah, so that's the final answer, that is p equal to minus 6 and q will be equal to 11 for the fourth question. Let's continue with the next one. The Rolle's theorem is holding good for the following function. So for x belonging to 1 by 2, show that the equation x log x equal to 2 minus x is satisfied at least by one value of x in the interval 1 to 2. Now see, if I say that there is an equation, say for example I give you a function f of x which is 5x square plus 2x plus 7, and I say that x equal to k satisfies the given function. If x equal to k satisfies the given function, or okay, now a function, let's give you an equation y equal to 5x square plus 2x plus 7, and I tell you that x equal to k and y equal to p satisfies the given function, it satisfies the given equation. If these values of x and y satisfy the given equation, you can put the value of y as p, so that will give you p equal to, and you can put the value of x as k, so that will give you 5k square plus 2k plus 7. Whatever values of x and y satisfy a given equation, you can put the values in the equation, and whatever you get is going to be a true relation. That's the logic that we will be using for answering the fifth question. That we will okay, let's first start solving and you will realize what I'm talking about. If this function satisfies all conditions of the Rolle's theorem, then there should be one point at least in that interval 1 to 2 where the derivative is going to be 0. So I will say that let that point be c, and f dash c will be equal to 0. Keep in mind, c is a point which belongs to the interval 1 to 2. Okay, f dash of c, that will be x minus 2 into derivative of log x, which is 1 upon x, plus log x into the derivative of x minus 2, which is equal to 1, and we are equating it with 0. This was f dash x, but we wanted f dash c to be equated with 0. So in place of x, we can write c. Now by rearranging the terms in this equation, so you can actually take this entire term on the right hand side. So that will give you log c, because that's the only term you're left with on the left hand side. On the right, it will be minus of c minus 2 divided by c. Take that minus inside, so you get 2 minus c upon c. And you can take that c on the left, so you will have c log c is equals to 2 minus c. And that's a relation that you have for a number c which lies in the interval 1 to 2. But if a number c is going to satisfy this relation, then we can say that x equal to c satisfies the equation x log x equal to 2 minus x. Okay, see, because if I say x equal to c satisfies this equation, you can put x equal to c in the equation and get the relation here. In this sum, we are doing the reverse of it. We had a relation, and because we had a relation for the point c, we had some condition that the number c will satisfy. We said that if number c satisfies this, then basically x equal to c is a value that satisfies this equation. But that number c was a number belonging to the interval 1 to 2. So we say that this equation is satisfied by a value c, that is, it is satisfied by at least one value which belongs to the interval 0 to 2. And that is how we are answering the fifth question. Going ahead with the sixth question, f of x is this. It satisfies all the conditions of Rolle's theorem in this particular interval. Find the value of c such that f dash c is going to be 0. It's nothing in this question. All you need to do is take a derivative, equate it with 0, and find the relevant values of x. So this is a function of the type u into v into w. the derivative will be f dash of c equal to 0, right? So the derivative f dash of c, that will be u v derivative of w, so that will be c plus 3 and e power minus c by 2 into minus 1 by 2 plus it's going to be u w and derivative of v, that is c e power minus x by 2 into 1 plus you have this and derivative of this, so that is e power minus x by 2. So instead of x we need to put a c because we are not writing f dash x, we are writing f dash c. Okay, the next term c plus 3 and derivative of x, that is going to be equal to 1, and we are equating this with 0. You can pull out e power minus c by 2 common from every term, that will give you c plus 3 and minus half. So you have minus c square minus 3c divided by 2 plus this has come out common and you are left with a plus c from this term, plus from here you are left with c plus 3. E power minus c by 2 can never be equal to 0 because any power of a positive number can never give you 0. So that e power minus 2 can be taken on the left and 0 upon e power minus c by 2 will be 0 only. We are left with minus c square minus 3c. Let's combine all the terms. So then you will have plus 2c. Okay, actually this will be 2c. So plus you will have 4c plus 6 the whole divided by 2 equal to 0. That 2 goes on the right. So you are left with this entire thing equal to 0. Now you have minus 3c plus 4c which is simply equal to plus c. And then you have a plus 6 equal to 0. You can multiply throughout with a minus 1. So that will give you c square minus c minus 6 equal to 0. Factorize it, so you have c minus 3 and c plus 2 equal to 0. So this tells you that the value of c will either be equal to 3 or c will be equal to minus 2. But the Rolle's theorem has been satisfied in the interval minus 3 to 0. So you will take only that value of c which belongs to the given interval, which is minus 2. And you will discard the value c equal to 3 because, like I said, it does not belong to the given interval. So the value of c is going to be minus 2 for the sixth question. Going ahead with LMVT, we need to verify whether LMVT is going to be, we need to verify LMVT. That is, see what LMVT tells you is that if a function is continuous and differentiable in a given interval, then there will be at least one point in the given interval where the derivative of the function will be equal to f of b minus f of a upon b minus a. Basically the slope of the line joining the extreme points. So here f of x is log x. In the interval 1 to e, the function is going to exist for all values of x. So we can say that f of x is continuous in the given interval which is 1 to e. And if you take a derivative of that function which is 1 upon x, you see that 1 upon x is also going to exist at every point in the given interval. 1 upon x will not exist when x will be 0, but x does not lie in the interval. So for every point lying in the given interval, f dash x is going to exist. And if f dash x will exist, we say that f of x is differentiable in the interval which is 1 to e. Let's now go for finding the derivative. So we will say that let's find a derivative f dash c in such a way that let's find a point c in such a way that the derivative at x equal to c, which is f dash c, should be equal to f of b, that is f of e, minus f of a, that is 1, divided by e minus 1. That's the term e. Okay. So f of e, f dash of c, okay, f dash of c will be 1 upon c. F of e, that will be log e, which is 1, minus f of 1, that will be log 1, which is equal to 0, upon e minus 1. So you have c is equals to e minus 1, and e minus 1 is going to be a number that lies in the given interval which is 1 to e. So yes, we do have a point in the given interval where the derivative is going to be equal to fb minus fa upon b minus a, and that is how we are verifying the Lagrange's mean value theorem. If some of you are confused as to why would e minus 1 lie in this interval, then let me tell you that E is approximately equal to 2.71828. So E minus 1 will be approximately equal to 1.71828, and that number definitely lies in the interval 1 to E. So yeah, you got the value of C that lies in the interval, in the given interval, and like I said, in the given interval, the value of C is such that FB minus FA upon B minus A will be equal to F dash of C. Let's continue with the next question, that is the second one. Here the interval is 0 to 4 and it's a polynomial function. Okay, when you expand it, you will get a cubic polynomial. So it is definitely continuous and differentiable in the given interval, because polynomial functions are continuous and differentiable over the entire range of real numbers. If the function is differentiable and continuous, it is satisfying all the conditions of the Lagrange mean value theorem. So we go for finding the point C in such a way that F dash of C should be equal to F of B, which is F of 4, minus F of 0 divided by 4 minus 0. F of 4, that will be 4 minus 1, which is 3, into 4 minus 2, which is 2, into 4 minus 3, which is 1. So we have 3 into 2 into 1, which is equal to 6, that is F of 4, minus F of 0. F of 0 will be minus 1 into minus 2 into minus 3, which is equal to 6 again, but actually it's a minus 6. So F of 4 minus 6 upon 4 minus 0, and this should be equal to 12 by 4, which is 3. F dash of C has to be equated with 3. F dash C is going to be obtained from here, that is, you take F dash X and F dash X. F of X is a function of the type UVW, so the derivative is going to be UV derivative of W, that is X minus 1, X minus 2 into 1. So we are finding F dash of C, right? So we will write it as C minus 1, C minus 2 into 1. Then it will be U W derivative of V, which is C minus 1, C minus 3 into 1, plus the last term will be V W and derivative of U, which is equal to 1. And we are equating that with 3. So if you factorize, if you expand all the terms, you have C square minus 3C plus 2, C square minus 4C plus 3, and C square minus 5C plus 6 equal to 3. Simplifying that, we have 3C square minus 3 minus 4 minus 5, that is minus 12C, and then there is 2 plus 3 and 3 from here get cancelled, and then we have plus 8 equal to 0. So to factorize that, the product is 24, right? So 24 and 2 numbers giving you 12, that should be okay, we don't have any such numbers, so we will have to apply the quadratic formula. So the value of C will be minus of minus 12, which is plus 12, plus minus root over B square, that is 144, minus 4AC, that is 4 into 3, which is 12, into 8, which is 96. The whole divided by 2 into 3, which is equal to 6. 144 minus 96, that will be 48. 48 is 16 into 3, and root over 16 into 3, that will be 4 root 3. Divide the entire equation with 6. You can't simply divide with a 6, but yeah, your 2 can come common from the two terms here, and you will have 6 plus minus 2 root 3, the whole divided by 3. I'll further divide that by 3, so that will give me a 2 here, and 2 plus 3 root 3 by 3, that will be 2 by root 3. Now the point is, we have definitely taken two values of C here, but do we need to eliminate any value? The answer is yes, because when you talk of the interval 0 to 4, the values of C that you take have to be compulsorily in that interval. You can take both the values given that both values lie in that interval, but if some value does not lie in that interval, then you need to eliminate it. So let's check what these values are. So 2 plus 2 by root 3. 2 by root 3 is 2 upon 1.732, and let's approximately take that as 1.7 so that we can get some approximate value for C. So that's 2 plus minus 2 upon 1.7, that's like 20 upon 17, which is 1 point. That would be approximately 1.2, a little lesser than that, but yeah, 1.2 approximately. So this is going to be something less than, so one value is 2 plus 1.2, something approximately 3.2. This 1.2 was a number which is a little larger than the value I have taken. So our first value of C will be slightly lesser than 3.2, and yes, it lies in the given interval. So 2 plus 2 by root 3 is an acceptable number. Let's check for 2 minus 2 by root 3. So when you subtract the two numbers, you get something like 2 minus 1.2, which is 0.8. This number is a little bigger number than the true value. So the number that you get will be a little bigger than 0.8. So if the number is going to be a bit more than 0.8, then a number little greater than 0.8 lies in this interval, and that is why we say that even the second value 2 minus 2 by root 3 lies in the given interval. So both the values of C, that is 2 plus minus 2 by root 3, are acceptable, and these values lie in the given interval. So at least there is one value existing in the given interval where that condition of f dash C being equal to fb minus fa upon b minus a will be satisfied, and that is how we are verifying the Lagrange's mean value theorem. Let's continue a little more quickly with the third question. So f dash of C has to be equated with f of 13 by 7 minus f of minus 11 by 7 divided by 13 by 7 minus minus 11 by 7. F dash of C, that will be 2C minus 3. That will be equal to f of 13 by 7, which is 169 upon 49. Then there is minus 3 into 13 by 7, so minus 39 upon 7 minus 1 minus f of minus 11 by 7, that will be 121 upon 49. Then minus of minus, that is plus 3 into 11, that's plus 33 divided by 7, and then ultimately there's a minus 1 again. The whole thing divided by, we have 24 by 7 in the denominator. So if you open up the bracket here, this becomes a negative value here, and this becomes plus 1. So minus 1 plus 1 gets cancelled. Minus 39 minus 33, that is minus 72 divided by 7. And this number will be 169 minus 121, that's 48 upon 49 minus 72 upon 7, and divided by 24 by 7 means multiplied by 7 upon 24. You can pull out a 24 common from the two terms here, and that will leave you with 2 by 49 minus 3 by 7, the whole into 7 upon 24. That 24 got cancelled. With the 24 we pulled out common from here. Open up the bracket with this 7. So you are going to have 2 by 7 minus 3, and 2 by 7 minus 3, that is that's 2 minus 21, which is minus 19 divided by 7. The value that we have just got is the value of 2c by 3. So when you equate that 2c by 3 with minus 19 upon 7, you have, okay, take that plus 3 on the right hand side, and you get minus 19 plus 21, which is 2 by 7. And when you cancel off that 2 here and here, you get the value of C as 1 upon 7. So the value of C, 1 upon 7, it lies in the given interval. And yeah, you have one value of C lying in the given interval where the condition of LMVT is going to be satisfied. Okay, so that's how we are verifying LMVT for the third function. I didn't do the first two steps, but I'll just orally tell you what they were. The given function is going to be continuous and differentiable in the given interval because it's a polynomial function. And yeah, because it satisfied the two conditions of Lagrange's mean value theorem, that is, it was continuous and differentiable in the given interval. There had to be a point in this interval where this LMVT equation would have been satisfied. Okay, so we got that value where LMVT was satisfied, and it lies in this interval. So we have verified LMVT for the third function. Continuing with the fourth one. Again, it's a polynomial function, so continuous and differentiable in the given interval. Conditions of LMVT are satisfied. The derivative f dash of C, that should be equal to f of 1 minus f of 0 divided by 1 minus 0. F dash of C, that will be 2 minus 2C. That should be f of 1, that will be 2 minus 1, which is 1, minus f of 0, which is equal to 0, divided by 1 minus 0. So we have 2 minus 2C equal to 1. Take that 1 on the left and take this 2C on the right. So you will have 1 equals to 2C, and C will be equal to 1 by 2. The value of C, 1 by 2, it lies in the given interval 0, 1. And yeah, that is how you are verifying the Lagrange's mean value theorem. That is, there's one point in that interval where the Lagrange mean value equation will be satisfied. Let's take this one last question for this video. So the given function, it is continuous and differentiable everywhere in the given interval. The only point where it would have been discontinuous is the number x equal to 3, but it does not lie in the given interval. So talking strictly of the given interval, the function is continuous and differentiable everywhere in the interval 4 to 5. So Lagrange mean value theorem conditions are satisfied. So try finding that point where the slope, that is the slope of tangent, that is f dash c, will be equal to fb minus fa upon b minus a, that is f5 minus f4 upon 5 minus 4. So f dash of c, that is the derivative of this, which will be c minus 3 into the derivative of x minus 1, which is 1, minus c minus 1 into the derivative of x minus 3, which is 1, upon c minus 3 the whole square. F of 5, that will be 4 upon 2, which is 2, minus f of 4, that will be 3 upon 1, which is 3, divided by 5 minus 4 is 1, c minus 3 minus c minus 1, that makes it c minus 3 minus c plus 1. So c and c get cancelled, minus 3 plus 1 will be minus 2, this will be minus 1. On the right hand side you simply have a minus 1, minus and minus also get cancelled, so here you are left with a 2, here there was a 1, this goes on the right, so you get 2 equal to c minus 3 the whole square. So the value of c will be equal to 3 plus minus root 2. Now root 2 is 1.414 approximately. So when you go for 3 minus root 2, you don't get a number in this interval. So 3 minus root 2 needs to be discarded, and the only possible value of c that you have is 3 plus root 2. You can check that for yourself. Root 2 will be something like 1.414. So 3 plus root 2 will be approximately 4.414, which lies in the given interval. So 3 plus root 2 is the value of c that you get in this interval. At that value, this particular condition, that is the LMVT equation, will be satisfied. That's where I'm done with discussing whatever I wanted to discuss in this video. I hope that the contents have been somewhere helpful to you in your preparations. Do check out other videos in this playlist. Thank you for watching.